Okay, so this screencast presentation is about waves, but instead of regular waves which you're used to in a mathematical format, sine, tangent, cosine, all that good stuff, it is instead about water. We all love water. Mr. J loves water, so I hope we get extra credit. Here's some pretty pictures of beaches and a big wave in the background. I mean, there's big waves, there's small waves, there's waves of all kinds, all shapes and sizes, several colors. It's nice. Okay, so the definition of a wave is a disturbance that travels through one medium from another location. Oh wait, from one location to another. However, excuse me, an ocean wave is a forward movement of the ocean's water due to the oscillation of water particles by frictional drag of wind over the Earth's surface. So if you have a lot of wind, you have a lot of waves. Easy as that. Now, the wind that blows over the top of the water creates friction, and the friction between the waves and the wind creates, well, between the ocean surface and the wind creates a wave. The speed, distance, and the length of time it travels over the water is greatly influenced by how big the waves are, which means it's greatly influenced by how large the wind is. Now, some natural phenomena like storms or like earthquakes or stuff like that can create even bigger waves, which we'll get into different kinds of waves later. But these choppy waves okay, so storms create giant choppy waves that become strong, smooth peaks called swells. And these swells drag across the crust of the ocean and produce more friction, causing waves to grow even taller until they break on the surface or the coastline. Now, the anatomy of a wave looks a lot like how you would picture a sine wave or a tangent wave, and if you want to know how that looks like, you can just put it on your calculator. So, the anatomy of a wave, it consists of crests, which are here at the top of the wave, otherwise known as maximum, and troughs, down here at the bottom, otherwise known as minimum. And this white dashed line is the water level at equilibrium. So if there was no waves whatsoever, that would be flat. And the wavelength is determined by the distance between the two crests or two maximum. So if there's more wind, there's probably going to be a greater wavelength. Also, wave height is the different distance between the crests and the trough. Oops, stupid Max. Okay, so sorry. Equation for waves is this big, giant, destructive equation, which probably will never be used. However, it's here for our convenience and enjoyment. If you look at the diagrams, it's basically a circle in an oscillating motion, and if you trace that over a period of time, then you get these waves, which mirror regular waves. And it's also called a trichoid curve. Now, the most simple wave is a sine wave, and here you have the basic equation for a sine wave. And this should be moving, but it doesn't. And this equation is universal for all forms of waves, including sound waves. So these also mirror not just ocean waves, but they also mirror sound, any other kind of wave you could think of. I'm pretty sure light is included in that. Now, in terms of physics, objects on the wave that wish to stay on the wave have to balance out two different forces, otherwise known as buoyancy and gravity. So a surfer, or Mr. Day, when he's shredding, has to keep his buoyancy and gravity at equilibrium when he's paddling out to a wave. However, when the wave catches up to him, he needs to adjust the surfboard underneath him by adjusting his gravity to move the board in sort of like a tangent form to the wave, and uses momentum to keep himself on the wave. Now, when he's riding the wave, he needs to go back to equilibrium. However, the forces between gravity and buoyancy need to be a lot smaller, so that way there's more balance and he doesn't fall off. Otherwise, he could look like this. I like this one. This one's my favorite. Now, a tsunami is much different. A tsunami is not formed on top of the water, rather it is formed underneath through the different kinds of natural phenomena such as like earthquakes, volcanoes, or other geological movements. These are the differences between a tsunami and an ocean wave. Now, a tsunami is the result of a huge displacement of large seawater and is caused by volcanoes, earthquakes, or other phenomena of the sort, landslides, and they travel at much faster speed, 800, compared to regular waves, 130. And there are also tidal waves, but those are a lot different to discuss, involving celestial movement and whatnot. So hopefully this cleared up a whole bunch of the stuff involving physics and what Mr. Day does best. And we'll see you in class.